Fundamental Theorem of Calculus, Part 1. So the idea, we saw this in the video, that if you had an integral from a to b, that would represent the area under the curve, which is between the curve and the x-axis, from a to b. So now we make a function. On the video they said g of x, I have I of x, doesn't matter what we call this function. But if we started at a and went up to some variable x, and x could change, we would get different variables based on different equations for x. The variable t is a dummy variable. It's important to be there, but we actually don't use it in the fundamental theorem of calculus. The idea is, well, if we wanted to find an area, we could use our Riemann sums, add up all those rectangles to find the area, and we could do that up to any variable x. Okay? Take out our highlighter. In order for the fundamental theorem of calculus to work, it's very important that the function is continuous and differentiable. So it only works when we have nice, straight, curvy functions that are continuous. So part 1. Since I of x is some function, well, we could take its derivative then, because it's smooth and continuous. So if we take its derivative, we take the derivative of the other side, and what we saw in the video is this simplifies so nicely just to be f of x. And this is true for any x anywhere, as long as that function is differentiable and continuous. So these questions, knowing that, part 1 of the questions are super easy. It's like, okay, so if I take the derivative of this integral up to x, this is fundamental theorem of calculus part 1, so things that you are going to start to notice, I'll take this pen out. If they have an integral with an x at the top, it's like, oh, that's going to be fundamental theorem of calculus part 1. Or you have a derivative of an integral and there's an x anywhere in that a or b part of your integral. This is going to be your fundamental theorem. And it's just a matter of, oh, so I just take this and replace the t with x. Yes, it is that easy. So we take the part that is inside here, and just that was your f of t. And the fundamental theorem says, well, the answer is f of x. So you just change your t to an x, and everything is straightforward and easy. Where the fundamental theorem gets complicated a little bit is what we saw at the end of the video. When we start not just having an x here, we have other value variables, x cubed, different things like that. So we'll look at that as well. But for the most part, okay, number at the bottom there, the 7. It could be 7 million. That number doesn't matter. And if you're going up to x, then the derivative of the integral is just f of x. So these first two are really straightforward, really easy. Recognize that it's the fundamental theorem of calculus part 1. There's really no math that you're doing. You're just writing an answer down based on what the fundamental theorem of calculus part 1 is saying. But if we go up to a value that is not an x. We're going to use some substitution and a little bit of chain rule to make this work out better for us. Okay? I think this is the easiest way to do it. It's like, this is a problem that it's not an x, right? Fundamental theorem of calculus only works if it goes up to x. If you do d dx and it goes up to x. So what we're going to do is we're going to say, I know I'm going to make u equal to x squared plus 1. Then the derivative with respect to x, if I did the derivative of this, du dx would be 2x. And here's the idea. Okay, I'll let you write this down. And then sometimes in calculus we have notation things that work out beautifully. This is one of those cases. And I'll talk a little bit about what actually happened as we go from here to here. Okay? Yeah, I've got an extra E on the chain there. Chain rule. Okay. So. I didn't have DDU. How can I change DDX to DDU? Well, I don't want the DDX on the bottom anymore. So with fraction rules, you see if you had a DX on the top, it would cancel with the DX on the bottom. But I want the DU on the bottom, so I'm going to need this. So if I want to have DDU, because if I have DDU and I go up to U, I have fundamental theorem of calculus part 1. Same as DDX going up to X. Same as DDW going up to W, right? We could pick any variable that we wanted. As long as we go up to that variable, we've got the fundamental theorem of calculus part 1. Okay? Problem here is I have ddx, but I don't go up to x. This is an issue. I can't use it unless this goes up to this. So I do a substitution rule. I say, well, let's make this a nice variable that we go up to. I'm going to call u x squared plus 1. Now I'm going up to u. And if I could do ddu of that, then it would be very nice and work out for my fundamental theorem of calculus part 1. So how do I change the ddu? Well, ddu, I had ddx. And so I want to get rid of my dx's to get ddu. Sort of fraction rules. Even though we're dealing with derivatives here, and there's actually a little bit more explaining to do to make this allowed. But for what we need to do for our class and for us making sense of this, we're going to say it's allowed. That these are just like fractions. And so do you see what I did? I took the ddx, I replaced it with ddu, and if I highlight things here, we replace this with this and this. We just wrote it afterwards. And it's like you're doing a chain rule because you have this function is inside of the other function, so you'd have to do the derivative afterwards. That's more of the explanation. But the easy way to see it is to think of fractions and say, okay, it makes sense for me with fractions. It works here as well as a chain rule. And then this just becomes, well, this part here in the red box, that just lets you rewrite this with u's, because that's the fundamental theorem of calculus part 1. And then we still have the du dx afterwards. And now we can substitute everything back to x. So the u is x squared plus 1, e to the x squared plus 1, and du dx has the 2x afterwards. And you can simplify this if you wanted. So a complete understanding of what's happening, we've got a chain rule happening. A simplistic way is what's in the blue box here, is like you're just rearranging some variables to make the formulas work. And it's really, this makes it quite simple. So let's look at our next example here. Ooh, I've got some issues. I've got the x on the bottom. And in fact, it's an x cubed on the bottom, so I'm going to have to do some substitutions. If the area from A to B is a positive number, the area from B to A is going backwards, is going to be a negative number. We're going to find out this. We're going to have a lot of properties of integrals. This is one of the properties of integrals that we're going to learn about. And just a quick, simplistic explanation of this. Okay, let's say I have some curve like this. We're going to think of the integral from A to B as if we could use the fundamental theorem of calculus starting from 0. You would have this blue area up to A would be the area from 0 to A. And this green area up to B would be the area from 0 to B. And if you took the two of those areas and subtracted them, you would get the area from A to B. That's a simple idea. If you subtracted them backwards, if you started with, right, here I'm saying I took the area up to B and subtract the area up to A. If I started with the area up to A and subtracted the area up to B, well then I would get a negative answer because I'm subtracting a bigger area. And you've seen this with numbers, right? 7 minus 5 is 2, but if I do 5 minus 7, I get negative 2. If you switch the order of them, you still get the same number, but if you subtract the bigger one from the smaller one, your answer is going to be negative. So this is this idea. So first of all, I can move my variable to the top by putting a negative up front. Second, oh, and this is missing a dt. Second, I can do a substitution. I can say u is equal to x cubed. So du dx would be 3x squared. And now I can write d du and my du dx at the end. And then that changes this. So that's our fundamental theorem of calculus. We still have the negative out in front. And then we have du dx. We do our substitution in the end. And we get our answer. The fundamental theorem of calculus part 1, except for a few questions on the AP exam, is hardly used. because it sets the stage for the fundamental theorem of calculus part 2, which is the huge groundbreaker for all of calculus. So, you will get some questions, simplistic ones where you just have to recognize, oh, it's the fundamental theorem of calculus part 1, and then chances are, in order, because the regular questions that we did first, right? Like, if I gave you an assignment of 100 of these ones, you'd be like, oh my goodness, this is the easiest. So all I have to do is take the red box and change it to an X. And you're like, yeah, wow, this is the easiest thing in the world. So then what happens is they're like, well, how can we make it harder? We had the chain rule idea. But you've seen with that substitution, that makes it not that. But that's the fundamental theorem of calculus part 1. Not super crazy. The idea, though, is super important because it leads us to the fundamental theorem of calculus part 2, which says if you want to find the area under the curve from a to b of some function little f of x dx, since we know the derivative is f of x, right? Fundamental theorem of calculus part 1 says if you take the derivative of this going up to x, you would get just the f of x inside. Then if you wanted to work backwards to find out what the actual equation was, you need to find the antiderivative or the integral. And so f of x is the integral of the inside. And then we write this notation from b to a, because the fundamental theorem of calculus part 1 said, well, if that's just the area up to b and this is the area up to a, if we subtract those two areas, we get the actual area in between a and b. And this is a lot easier than calculating a whole bunch of rectangles with Riemann sums. Thank you, Riemann, that you can go to bed. We don't need you anymore. So here's how simple it is. We find the indefinite integral, which we call the big f of x. We write our result in square brackets with that integral going from a to b. Then plug in b, plug in a, and we get a numerical value. And you have stuff on your calculator as well, where you can calculate integrals and get actual values. And here, we'll pull out our calculator, show you a couple things. All right, let's do, oh snap, that's fun. Well, maybe we'll do something if it lets me close this. All right, so there's close. Ooh, that looks like a. Oh, we'll do something simple. Let's just do our regular parabola, x squared. There it is. And let's look at the area from 1 to 3. So a couple ways we can do this. We can go second trace, and number 7 here has the integral. So I push enter, and this is, where do you want to start? I said I wanted to start at 1. What did he want it to go up to? I wanted to go up to 3. And it shades it in for me and tells me the area at the bottom. I really like that because it gives me a visual of that area and tells me what the answer is. Okay. We can also get this same answer under the math button. And number 9, integral. And we can go from 1 to 3. I can type in x squared here, or I could type in y1 because I have it written in y1. But since x squared is super easy to write, I'm going to write that. And our variable is x, so we do d dx. And we get the exact same number this way as well. So I kind of like the graph part because it actually shades it in for me. It will cue me in, like if sometimes the area is underneath the curve, it'll cue me in that that's a negative accumulation of change. So these are quite helpful for us for finding the area if we have our calculator. And there will be definitely ones where they check if you know how to find those areas with your calculator. Okay. So we could draw this from 2 to 5 of 3 over x on our calculator and get that answer. If we didn't have the calculator and we were asked to find an exact value of this, did you recognize that the integral of 3 over x was the natural log one? It's always the hardest one to see. So this is going to be 3 natural log of x as the integral. We write that integral in a box and we write the bounds a to b from 2 to 5 afterwards. Then the fundamental theorem of calculus part 2 says, instead of adding up all those rectangles, all you have to do is plug in 5, subtract, plug in 2, and you get the same answer. I don't have to write that window down, just showing you that I went from -5 to 5. And what would they do maybe on the exam in multiple choice? They might play around with log laws here. Can you see that this is the same as natural log of 5 cubed minus natural log of 2 cubed? Which they could play around with this and say, oh, if you're subtracting, you could write this as 5 cubed over 2 cubed. Which you could write it, oh man, you could just keep having fun. I don't know. You could just keep making up log laws to come up with hundreds of different possibilities for what the answer shows up in the multiple choice. Will they do that? Yes. Right? They're like, you do not have to simplify when you're doing your work. So when you're doing your work, you could leave it like this and get full marks. But in the multiple choice, that's when they can have fun with manipulations to see if you know all your math skills really, really well. Look, sorry, but just take this in. This answer is exact. How much quicker was that compared to adding up little rectangles forever? It just simplified the process like unbelievably. The fundamental theorem of calculus part 1 says, well, if you went up to any x, then the derivative of this would be just this. And if the derivative of this is just this, then working backwards, if that derivative is gone, I'm going to need to have the original function. And when we do that original function, normally you would have had 3 natural log of x plus c. Remember when we always had the plus c? But if the one of them had a plus c, and the other one, when we subtracted it, had a plus c, well, Well, you're subtracting, the plus c really does not matter because you're subtracting. So now we just can ignore the plus c if we're doing a definite integral. Because if it was there, it would just subtract anyways and go away. So here, we want to find the integral from 2 to 4 of x plus 1 over x squared. Again, we don't have a ton of integral rules. I mean, you have all your major functions that you've learned that you can work backwards of, but we don't have any product rule, any quotient rule, any chain rule. We don't have any of those skills for integrals. So this is a function inside of a function. We don't have rules for that yet for integration. So you would actually have to multiply it out to get it into a form that you can do. We do have an integral rule that says you can do each of these individually if you're adding or subtracting. So we put a big set of square brackets. The integral of x squared, x cubed over 3. Integral of 2 would be 2x. Integral of x to the minus 2, just do it off to the side here. X to the minus 2. Add 1 to the exponent, divide by the exponent, so we would get negative x to the minus 1, or 1 over x. Put it in square brackets right from 2 to 4. Then take the first one, plug in 4. Subtract, take the second one, plug in 2. Simplify. And you get approximately 22.9, exactly 275 over 12. There were some questions on your take-home quiz that had this idea of the fundamental theorem of calculus part 2, where you had to do f of b minus f of a. Now that you've seen that, life gets easy. Okay, the danger though is forgetting how to do all the rectangles and the notation with the rectangles. Because this is way easier, right? But they're still going to ask you to do Riemann sums and approximations on your exam. So it's really important that you still get that notation down and understand what's going on. Here's a picture. There's the window that I used. Yes. Sorry?
Why is there
Just units squared. Because we're doing area. It would have units. What those units are, we don't know in this situation, but it's just doing units squared to show it is an area there. We'll do one more. Can you integrate each of these? Okay. Yes, we can. And then, do we remember what we had to do when we integrated? If there was a simple chain rule with the derivative where you had to multiply by 3, then there's a simple integral chain rule when you work backwards that we have to divide by 3. So we're going to get e to the 3x, but we'd have to divide by 3. The second one would be natural log of x plus 1. It is a function inside, but you see the derivative of the function inside is just 1. So technically you'd have to compensate by dividing by 1, which there's no compensation. So I didn't show anything, but if you wanted to, You could draw a line here and divide by 1 to show that you knew that there was a chain rule and you divided it. So we figure out the integrals, we write it in square brackets from 0 to 1, then we set up two big square brackets, subtract in between, plug in 1, plug in 0, and subtract the 2. On the exam, you could leave your answer like this and get full marks. On all the assignments that we give you, we still want you to simplify and get a final answer. Okay, so I would expect you to do this next step, combine your like terms, know that natural log of 1 is equal to, remember mental math? Natural log of 1 is 0. So that's why, I'm going to put an arrow here, that's 0. That's why it went away in my next step. And we get 4.98. What did we just figure out? Here's the picture. That's what that graph looks like. And we figured out that that area between 0 and 1, adding up all those rectangles, is 4.98. And when you think of it that way, as we can now find areas under any weird shape, every single function that we know how to graph, or a graphing calculator can graph, we can now find that area, is quite a phenomenal result.